Welcome. In this video, we are going to talk through the post-lab questions for the Le Chatelier lab, the rainbow lab that we did in class. So question 1A, write the equilibrium constant expression for this reaction. Whenever you write a K expression, in this case it's a Kc, so I'm going to use the square brackets. If it were a Kp, I'd use the symbol for pressure. And it's always products over reactants. So I'm going to write the products first. And the coefficients become exponents, and then you leave out solids and liquids. So we don't include the reactant because it is a solid. So that is our Kc expression. And you might find from other readings or videos you've done so far that in this context, this is also known as a KSP. The SP stands for solubility product, and we call it that whenever the equilibrium system involves a solid reactant dissolving in water to form ions. So that's what this system is describing right here. What would you expect to observe if hydrochloric acid is added to this solution? So first you have to consider what form hydrochloric acid takes when it's in water. We know that soluble ionic compounds and acids will both dissociate to form ions when you place them in water. So really when we add HCl, we're adding H plus ions and Cl minus ions. We want to look up here at this reaction system. I don't see H plus or Cl minus as being part of my reaction. Then you want to keep an eye out for other kind of side reactions that can happen. There are two main side reactions that you want to look out for. These are both double displacement reactions, if you remember from Unit 4. One of those is a precipitation reaction. The other one is a neutralization reaction. Precipitation reaction is when two ions, aqueous ions, come together to form a solid. Here's an example: silver ions and chloride ions combine to form silver chloride. You are able to predict whether they will form a solid or not just based upon your solubility rules. And then the other one is a neutralization reaction, which is when hydrogen and hydroxide ions combine to form liquid water. And the hydrogen ions come from an acid, the hydroxide ions come from a base. So those are two reactions to keep an eye out for. So H plus Cl minus, not part of our equilibrium. So you can ask yourself, well, what else could be happening here? Well, the Cl minus could potentially combine with the calcium, and that would form CaCl2. You want to think about your solubility rules and ask yourself if CaCl2 is soluble. And it turns out the things that are soluble include alkaline metal compounds and nitrates, and most chlorides are soluble. The only time chlorides are not soluble is if it's bonded to like silver, lead, or mercury, like we have over here. So calcium chloride is actually soluble, so this will not form a precipitate, so that reaction won't happen. So now let's take a look at the H plus. Well, the H plus could react with a hydroxide that's up here, and that will form liquid water. So what happens is this reaction occurs. That is going to remove hydroxide ions from the solution because they're going to react with the hydrogen and form water. So your amount of hydroxide is going to go down. And your hydroxide ions are a product in this reaction. So if we remove them, the reaction is going to shift to the right. Over here, we're adding an aqueous ionic compound. So just like an acid, it is going to split apart into ions. And notice in this case, one of these ions is directly found in our equilibrium system up here. So you are adding calcium ions, which are a product. So the reaction is going to shift to the left in order to use up that excess product that you added. Okay, because the system's going to react in order to try and restore equilibrium. So if you took away product, it's going to shift to make more product. If you add too much product, it's going to shift to use up that excess product. If we look at this scenario, this is saying we, make some observations. We place the solution in an ice bath. So ice bath means we're removing heat. And it's observed that more solid is formed. So when you remove heat, we make solid. If we look back at our reaction, it looks like the solid is the reactant. So that means that when we remove heat, we end up making reactant. And we want to know if it's exothermic or endothermic. So the one way to do that is you could think through your scenarios. So what if it's endo? What if it's exo? If it's endothermic, heat behaves like a reactant. If it's exothermic, then heat behaves like a product. If, in the first scenario, endothermic, if we remove heat, then the reaction is going to shift to the left to produce some more of that heat that we just took away. If it's exothermic and we remove heat, it is going to shift right, again, in order to replace some of that heat that we removed. What we saw is that when we removed heat, it made reactant. Therefore, it looks like this reaction is endothermic. Because if it's endothermic, removing heat would cause the reaction to make more reactant, which is what we saw happening here. Based on that, if we were to place it in a hot water bath, so if we were to do the opposite, right, and add heat, we would expect the reaction to shift to the right. And it is going to dissolve more. So you'll notice that some solids, when the dissolving process is endothermic, if you add heat, if you heat them up, they'll dissolve better. Some solids would dissolve in water exothermic. In that case, if you add heat, they will actually dissolve less. Let's look down at this one. We've got this reaction system. What impact will increasing temperature have on this system? So your reaction is endothermic. So that means heat is behaving like a reactant. So when you add heat, the reaction is going to shift to the right in order to use up that excess heat that you added. If you decrease the volume, what will happen? So I need to look at my gases. Over here, it looks like I have 1 mole of gas on the left, and it looks like I have 2 moles of gas on the right. So if I decrease the volume, that means I'm increasing pressure because volume and pressure are inversely related. And when the pressure increases, that means, oh no, the pressure is too high. Your system's going to try and respond to reduce the pressure. So in order to reduce the pressure, it is going to shift to the side with fewer moles of gas. So if the pressure goes up, it's going to shift to the side with fewer moles of gas in order to reduce the pressure. If the pressure was too low, it would shift the other way. So in this case, since the pressure has increased, it's going to shift to the side with fewer moles of gas, which is the left, it looks like. So it's going to shift to the left. What impact will adding liquid bromine have on the system? Well, initially you might look at it and say, oh, it's obvious. You're adding reactant, so it's going to shift to the right. But if you take a look at the K expression for this, let's look at like a KP expression. It would be BrCl squared and then Cl2. And notice how bromine is not included in the K expression because it's a liquid. So you leave liquids and solids out of the K expression. And the reason why adding a reactant or product causes an equilibrium shift is because it gives you a scenario where Q is not equal to K. And as a result, your system has to shift in order to get back to equilibrium. But if you're adding liquid bromine is not part of my K expression. So adding liquid bromine does not affect my Q value. So that means that if I add liquid bromine, I'm actually still going to be at equilibrium. So there's going to be no shift here. So what that means is that if you're at equilibrium, adding or removing liquids or solids will have no impact. It will not cause an equilibrium shift. And the reason why is because it does not change your Q value. So when we're at equilibrium, Q is equal to K. If I add more bromine, Q is still equal to K. So I'm still at equilibrium, so no shift is going to occur. So this is kind of, a special case here. And this one, removing chlorine gas. Chlorine is part of our K expression, so removing that will have an impact. So if you remove Reactants, it is going to shift to the left in order to replace those reactants you removed. Adding a catalyst will have no impact on your equilibrium. You will just reach equilibrium faster if you add a catalyst, but adding a catalyst will not cause an equilibrium shift. All right, hope that helped. Send me a message if you have any more questions.